Just 1 second and I'll tell you. Okay.
You ready?
Yeah.
Yeah. Okay. I'll start then.
Yes.
Yeah. Okay. So hello everyone. Thank you for joining this session of the virtual seminars in economic theory. We are very glad to see all of you again. Today we have Alessandro Pavan from Northwestern, who's going to give a presentation on expectation conformity in strategic reasoning. We are very pleased to have with us Alessandro's co-author Jean Tirole and the two guest panelists, Tommaso Denti and Muhamet Yildiz. Just to remind you quickly the format of the seminars. We have a 60-minute presentation with time for interim questions from the panelists, followed by a 15-minute session for questions and discussion. We kindly ask all attendees to keep microphones muted during the talk. You can post comments and questions in the chat. Jean will answer clarifying questions in writing and pass more substantive ones to Alessandro, I believe. There will, of course, as always, be another opportunity to ask questions live in the Q&A session at the end. And just to remind everyone that the talk is recorded. Before I hand over to Alessandro, let me remind you that these seminars take place every Thursday at 4 p.m. UK time. Next week, we will have with us Amanda Frindenberg from Arizona, talking on two approaches to iterative reasoning in games, which is a joint work with Adam Brandenburg and Terry Neeland. And the guest panelists will be Emiliano Cantonini and Paul Healy. As usual, you can find more information about the coming list of speakers on our website or by following us on Twitter. And without much further ado, give the screen to Alessandro. Thanks a lot. The floor is yours, Alessandro.
Thanks a lot to the organizers for inviting us. So as Miltos was mentioning, this is joint work with Jean Tirole, and we are lucky to have him with us today. So let me give you a little bit of preview of what motivates this work, and then I will move to the heart of analysis. At a very broad level, we are motivated by the observation that there are many strategic situations of interest where the player's understanding of a game before playing it is endogenous. And the endogeneity may have different forms. It may originate in different channels. You may think of the players as acquiring information about the consequences of their own actions and the actions of others in the form of learning about payoffs. You can also think of players trying to better predict the possible behavior of others by investing in understanding how other players are likely to interpret the game. And that may take the form of acquiring information about possible beliefs that other players may have about the underlying game before playing it. But also cognition can and should be interpreted more flexibly. For example, it can take the form of memory management. So players may invest in order to understand how come that they end up in a certain situation of interest. It can also take the form of endogenous depth of reasoning, reflecting the idea that perhaps the payoffs are known, but the best responses are not. And the players can spend cognitive resources in order to iterate over the computation of the best responses in an attempt to identify what is best for them in response to the predicted behavior of others. Depending on the environment of interest, cognition could either be self-directed, meaning it could take the form of investments that affect a player's own understanding of the game, such as when players acquire information themselves about payoffs or about the view of others. But it could also be manipulative, reflecting the idea that the players may engage into cognitive activities with the intention of affecting other players' view of a game. So examples of manipulative cognition include framing. So think about firms investing into the design of a contextual purchasing experience with intent of influencing the behavior of buyers. For For example, that can take the form of associating a product with experiences that the buyer may have undertaken in the past, or trying to conceal elements of the past that may affect negatively the purchasing experience of the buyer. More broadly, you can think of signal jamming as another example of manipulative cognition. So think, for example, of career concerns where workers engage into effort with the idea of manipulating the beliefs that the labor market has about their own productivity. It could also take the form of strategic disclosures or noisy communication, whereby players share information with others before playing the game. It could also take the form of defensive measures, where instead of sharing information with others, a player puts in place defensive measures to make it difficult for others to predict how the player will play the game. So think, for example, counterintelligence in the context of industrial espionage as a way of protecting the outcome of research that the firm conducts before engaging into a market game, in an attempt to make it difficult for competitors to spy and then play the game under superior information. So what do we do in this paper? We develop a framework that permits us to touch upon some of the issues that I mentioned in the previous slides. So we're particularly interested in understanding how cognition is affected by the type of strategic interaction under consideration, in particular whether actions in the primitive games are strategic complements or substitutes. But we're also interested in understanding how the choice of a cognitive posture reflects hierarchy of beliefs over the selected cognition. So we develop a notion of expectation conformity that is meant to capture the idea that the cognitive choice of a player often reflects the player's beliefs over the expectations that his or her opponents may have about the player's own cognition, as well as the player's beliefs over the actual cognitive choices of his opponents. And we're going to argue that the interaction between these two types of synergies is going to play an important role in these games. In particular, it can be useful to shed light on a few things. One is the determinacy of equilibria. So in particular, when is it the case that the equilibrium is unique, and when instead it's the case that the equilibrium is prone to multiplicity. And some of this multiplicity may take the form of cognitive traps, whereby players may end up spending a lot of resources in cognitions because they are expected to do so. And nonetheless, at the end, they end up with lower payoffs compared to a situation where they could commit themselves to engage in less cognition. And we're also interested in understanding how this expectation conformity measure relates to the type of strategic interaction under consideration, and permits you to shed light on the choice of the cognitive postures without necessarily computing the fixed points. So we're going to argue that part of the contribution of this notion of expectation conformity is that it really informs you about the driving forces at play without asking you to compute the equilibria. So computing the equilibria of these games often is daunting, it's very complicated. These are games that may be complicated even for given cognition, and it's even more so when cognition is endogenous. But understanding of interaction between the two synergies that I was alluding to a moment ago often sheds light on what shapes the cognitive choices without asking the analyst to compute the fixed points. So we see the contribution of the paper as twofold. First, in shedding light on how this notion of expectation conformity plays a major role across a variety of applications. And second, in bringing apparently different cognitive environments under the same umbrella, conceptual umbrella, which in turn permits us to shed light on what is in common across a variety of cognitive games, and also what makes a certain type of cognition fundamentally different from others. So because time is limited in this talk, I won't spend time discussing the related literature in detail. I will just mention blocks of strands of literature that are somewhat related to what we do. And of course, I apologize for not citing all of the work that we should. In part, that is due to the fact I wanted to fit everything in a single slide, and in part is due to the fact that because of cognitive limitations, at least on my part, I should not talk for Jean, I'm sure that I miss important references that I should have not missed, or we should have not missed. So please feel free to reach out after the seminar and indicate work that is related and which is not cited. So the paper, of course, is related to the literature on information acquisition in games. That's a broad literature. Information acquisition has been examined in the context of auctions, mechanism design, contracting games, security design, linear quadratic games, and global games. There's also literature on interpreting other players' view of a game and sharing information prior to playing. And some of the people in the audience have contributed importantly to this literature. The work that you're going to see today is also related to the literature on signal jamming and framing. There's also literature on sparsity and endogenous depth of reasoning that perhaps you're less familiar with. And because of that, I'm going to spend a lot of time talking about sparsity and endogenous depth of reasoning as examples of the type of cognitive games the analysis applies to. And lastly, the paper is also related to the literature on psychological games as pioneered by Giannakopoulos and others, and recently developed by Battigalli, Duffenberg, and others. So the main difference is that in this literature on psychological games, intentions and beliefs more broadly directly enter into payoffs over and above the implications they have for the selection of the actions of the players. Whereas in the analysis that we focus upon, beliefs matter only insofar they are instrumental to the selection of the actions in the downstream primitive game. So the plan for the rest of the talk is that I'm going to set up a model that I'm going to use extensively in order to talk about expectation conformity and its role in the selection of the cognitive postures. I will then define formally what we mean by expectation conformity, relate the notion of expectation conformity to equilibrium determinacy, establish that expectation conformity does not play any significant role in constant sum games, and then give you essentially a couple of examples of cognition in non-constant sum games. So in the paper, we also touch upon other themes, but today I will focus on sparsity and framing as examples of self-directed cognition and manipulative cognition, respectively. And then I will wrap up with an example of an environment where cognition is not about learning about an underlying state, but it's about understanding how to compute iterated best responses with the attempt of identifying the action that maximizes the payoffs. All right, so that's the plan. So here's the model. So I want you to think of a primitive strategic situation of interest as a downstream game that involves n players. These players are going to be denoted by little I, and the set of such players is capital I. Each player has an action set, AI. So this is a primitive of a game. Each player also has a payoff, little ui, that depends on the mix action of player I, which we denote by alpha I. It depends on the mix action of her opponents, alpha minus I, and it may depend on some unknown state of nature, omega. It's believed that omega is drawn from a set capital omega according to some prior distribution F. Cognition may mean different things. I wanted to start thinking of cognition as a flexible way of learning about payoffs. Later in the talk, I will also talk about alternative notion of cognitions. So think about cognitions as resulting into a vector of investments, rho I, rho minus I. And these investments may take different forms depending on the particular context and examination. Cognition is costly, so there's a cost Ci rho I for each of the player. The interpretation and the properties of such cost vary across environments. You can think of cognition as determining the partition of the underlying state space a player has access to. And in fact, if cognition is self-directed, that's as general as it can be. When cognition may also have a manipulative nature, instead of thinking of it as partitions, which has some problems, it's best to think of manipulative cognitions as determining the outcomes of a collection of experiments. So the way we capture this is as follows. There's going to be a distribution Q over some flexible set of signals S. Each S is a vector of signal where the different components correspond to the beliefs that are generated for the different players. The distribution of such beliefs depends on the underlying state, omega, and the cognitive postures of the different players, rho. Okay, so capital S here is the product of the SI. Rho is the vector of cognitive investments made by the players. The case of self-directed cognition is the special case where there exists a collection of QI such that the joint distribution can be written as the product of the different QI. So self-directed cognition has two ingredients embedded into it. One is independence, and the second is that each distribution QI depends on the player's own investment and not on the investment of others.
So Alessandro, can I ask a question before you go?
Yeah.
So especially, when we talk about this, counterintelligence measures. So here we assume that rho is like, in a way, pure strategy, pure action. So is this enough to, introduce, uncertainty about your own, what you are doing, your cognition levels? Is it, like, obviously you have proper distribution on S's, so maybe it's enough, but can you comment on that a little bit?
Right, so throughout the analysis, we focus primarily on pure strategy equilibrium. There are only a couple of exceptions in the paper. There are instances where this matters. So for example, suppose that the downstream game is an extensive form game as opposed to a normal form game. Then if you were to mix on your cognition and then take a sequence of actions in the downstream game where some of them are observable by your opponents before they act, then the actions that you take in the downstream game before your opponent act may reveal information about the realization of your mixed strategy, which is something that is interesting. So that introduces signaling in cognition, but we don't examine it in the paper. In fact, I will mention that towards the end as one of the things that I think is important to do in future work. There are other instances where mixed strategy are not so important. In particular, if there is no way for your opponents to learn anything about the realization of your mixed action other than what they learn by the observation of a signal S. So what you're alluding to is that when players get to see the signal, because they signal in the manipulative case depends on the cognitive choices of others, the realization of the signal carries information about the realization of a mixed strategy of others. So if the downstream game does not involve multiple rounds of actions, there are instances where the distinction between pure strategy and mixed strategy, it doesn't really make a major difference. But signaling, for example, and out of equilibrium beliefs and the like, is an instance where instead the two make an important difference. Yeah. Does that help, Muhamet?
Yeah, definitely.
Sure. All right, let me move on. So now think about the stage 2 game as being summarized by a collection of strategies for the player, sigma I, that map the beliefs that the players have, SI, into a mixed action. As Muhamet was saying, when you receive a signal S, you update your beliefs both over the payoffs, the payoff state omega, but you may also learn about the beliefs of others as well as the cognition of others. All of that is embedded into the Q function that I was describing a moment ago. And that's what Muhamet was asking about. And fixing a cognitive vector rho, suppose for a moment that this vector rho is common knowledge among the players. if a vector rho of cognition was commonly known, you could map that vector into a stage 2 BNE. Okay. It could be that the game for the same cognitive posture rho admits multiple BNE, in which case some selection will have to be invoked in order to predict the associated payoffs. Cognition is covert, meaning that the players may have beliefs over the cognitive choices of other players, but they don't get to see the cognition that other players undertook. There's an ex ante gross payoff that depends on the way players are going to play the downstream game sigma and the cognitive postures rho. So this ex ante gross payoff is nothing else but the average over states, or the average over the induced beliefs, which originates from the state and the cognitive profiles rho. And then given the realized beliefs, you use the sigma strategy profile to determine the mix actions of player I and his opponents. We're going to play a lot with the function vi. This function vi is a value function that determines what happens when it's expected that players engage in cognition rho, and player I instead deviates to cognition rho I prime. When the player changes his cognition, multiple things happen. First of all, the player affects the distribution of beliefs for himself and others. Second, when the player changes his cognition, most likely the player is going to change the way he's going to respond to the beliefs that the player himself is going to generate for himself, and is going to optimize again. So the value function internalize all these channels. The net ex ante payoff of a player is what is determined by the gross payoff of VI, net of a cognitive cost. And again, work has been done by Tommaso and others to provide, for example, a decision theoretic and micro foundation for games with endogenous cognition to take an additive structure where part of the payoff can be attributed to the gross value of cognition, and part of the payoff can be attributed to the cognitive cost of cognition.
Alessandro?
Please.
A question about the assumption of covert information acquisition. I guess, depending on the applications, I guess is going to be relevant covert or instead something that is, but more methodologically, given what you're doing sort of like in this paper, I was wondering, in principle, if it's not covert, if kind of like these choices are revealed, then you have a clear kind of like two-stage game, and kind of like the question that you can ask in a paper like this one is how basically the structure of the stage game in the second influence the structure of the first stage game. And now sort of like in the first stage, you have a well-defined game over these rows, especially because you are essentially assuming unique equilibrium after the rows. So basically you don't have even kind of like problems with some imperfection. And so, at least from a methodological perspective, seems also a natural choice. So I wonder why you went with the covert assumption.
I think, as you said, depending on the type of application you have in mind, you may favor the covert or the overt. So for example, if you're thinking about cognition as spending resources to learn about events, it's unlikely that you can see, how another player is going to, attain from different information sources to learn about a relevant event. If instead you're thinking about a firm, for example, putting in place a certain type of measures in order to learn about cost and or demands, then in some environments, perhaps such investments are observable by competitors before competitors act. But as Muhamet was saying, even when cognition is covert, there's still the possibility in this framework to get to learn about your opponent's cognition through Q. That's, I think, what Muhamet was alluding to at the beginning. So the realization of the signal S may carry information about the decision rho entertained by the competitors. So there is a way for you in this framework to learn imperfectly about the choices of others. Okay, but in terms of what is more reasonable, which is what I think you were alluding to, it really depends on what type of games you have in mind. So let me now move to the notion of expectation conformity. So I want you to think about expectation conformity as a diff and diff analysis. So don't be scared. So you're not going to see any reduced form regressions along the lines of what you see in the diff and diff literature, but the spirit is very similar. So we introduce the notion of expectation conformity as follows. Take a two cognitive profile, row and row hat. We're going to say that expectation conformity holds for this cognitive profile if the following is true. If the value for player I of going from cognition row I to cognition row I hat is larger when other players expect him to go into cognition row I hat and themselves adapt to that expectation by choosing cognition row minus I hat, relative to a situation where he's going from cognition row I to row I hat, but he's expected to choose cognition row I, and his opponents themselves are expected to choose cognition row minus I. So the idea of expectation conformity is that the value of choosing row I hat is higher when you're expected to choose that cognition, and the other player themselves adapt to the cognition accordingly, than when you're expected to choose another cognitive level, and the opponents also choose the corresponding cognition level. Now, expectation conformity itself may originate in the interaction between two types of synergies. And part of the contribution of the paper is to spell out exactly how these two types of synergies interact one with the other. The first synergy is a notion of unilateral expectation conformity. So fix the cognitive level of your opponent. Suppose that your opponents hold the cognition fixed at row minus I. And ask yourself, how does your payoff vary if you go from cognition row I to cognition row I hat when you're expected to choose cognition row I hat, relative to a situation where you're expected to choose cognition row I? So unilateral expectation is meant to capture the effect on your payoff, internalizing how you predict yourself and your opponents will play when you vary your cognition in an anticipated way relative to a situation where you vary your cognition, but you're expected to choose something different. A second force that shapes expectation conformity is what we call increasing differences because of its connection to supermodular games. Although it should be clear that here no lattice structure is imposed on cognition. Now this time, hold fix the expectation that your opponents have about your own cognition. As you can see, all these terms are the same. And ask yourself, how does your payoff differential when you go from cognition row I and row I hat depends on whether your opponents are choosing cognition row hat or row minus I. All right, now I wanted to relate the notion of expectation conformity to equilibrium determinacy. If expectation conformity holds for a pair of cognitive profile row and row hat, you can identify cost functions such that both row and row hat are equilibrium profiles. Furthermore, if cognition is self-directed, meaning that each player's investment affects the player's own understanding of the game and not other players' understanding of the game, and if a collection of information structure can be ordered, if you were to think of them as partition, think of them as order along the lines of whether one is finer than the other, or you can think of a Blackwell order over the cognitive choices. So if cognition is self-directed and totally ordered in the Blackwell sense, then if each row I is Blackwell more informative than the corresponding, if each row I hat is Blackwell more informative than a row I, then the cost themselves can be taken to be monotone. So what's the value of this first result is to shed light that in many games of interest, it's likely that the analyst has information about the benefits of entertaining different cognitive choices. It's less likely that the analyst has information about the cost. What this result is telling you is that if a game admits expectation conformity with respect to two cognitive profiles, the analyst should not rule out the possibility of multiple equilibria unless the analyst has particular information about the cost to rule them out. The theorem has also a counterpart. Suppose that expectation conformity is never satisfied for any pair of profile rho and rho hat. Then the equilibrium is unique no matter the cost functions.
Alessandro?
Yep.
I'm much in favor of this approach of thinking about what happens across cost functions. But once you take that perspective, maybe the fact that the equilibrium is unique or multiple for one cost function is in some sense a bit less relevant, in the sense that what you would like to do is to characterize all equilibria that can arise for any cost function in some sense, right? So
I would say, yeah, both. So there are instances where you may have a good sense of what the costs are, in which case you really want to characterize the equilibrium set for both cost functions. But there are also instances where, for example, you wanted to play with this second part of the result and argue that, look, the type of strategic interaction is such that no matter the cost functions, equilibrium is going to be unique. And one way to prove that that's the case is to verify that expectation conformity is never going to apply to any pair of cognitive profiles, rho and rho hat. So, it really depends on applied work, and how much information you have about the cost and what you're really trying to do. Are you trying to establish a negative result, a positive result? It depends.
So I also have a question about the second part. Have you looked at how difficult a condition it is? Because it seems that it is like the conclusion is extremely strong. So, in the second part.
Well, yes, and I will give you an example in a moment. I agree. So there are instances where it could be very daunting to verify that expectation conformity is never satisfied across any profiles. But there are also games where you could arrive at that conclusions in fairly simple terms. So I will give you an example of such games in a moment, which are constant sum games. So before I do that, let me wrap up this part by introducing the notion of a cognitive trap. I'm going to say that a cognitive trap arises if the following things are true. Suppose cognition is self-directed and cognitive profiles are totally ordered. I'm going to say that players are exposed to a cognitive trap if there exist two profiles, rho and rho hat, such that both rho and rho hat are equilibria, and the following is true. For any player for which rho hat is different than rho I, and rho hat Blackwell dominates rho I, the player is left with a lower payoff in the equilibrium with a higher cognition than in the payoff with the higher cognition. So there are instances where cognition is something which is largely driven by expectations. Players are forced to learn a lot about the game, but we end up with low payoffs, largely due to the expectation of others. Okay. Now I wanted to give a benchmark and then move away faster from this benchmark because it's not particularly interesting. So this is a benchmark of a class of games where cognitive expectations never lead to multiple equilibria, or if multiple equilibria emerge, they are sort of trivial. So consider the class of constant sum games. So these are games where, and specialized analysis to the case where you have two players. These are games where in each state of a word, there's going to be a constant that may depend on the state of a word, with the property that the sum of the two players payoff, it's pinned down by the state itself. And remember the definition of diff and diff and payoff differentials. So take any cognitive profile, a rho and rho hat, the sum across players of the payoff differentials is always negative. What that means is that either the equilibrium is unique in these games, or if there are multiple equilibria, then in any equilibrium, the player is indifferent between choosing the cognitive level that he's supposed to choose in that equilibrium and the equilibrium cognitive level that he's supposed to choose in another equilibrium. And the reason is that, well, if you think about constant sum games, the mere nature of constant sum implies that whenever the differential is positive for a player, well, there are forces that are at play, that make it impossible for the payoff differential to be strictly positive for that player, and at the same time respect the constant sum nature of the game. So that means that it cannot be the case that there are two profiles, rho and rho hat, for which expectation conformity holds. If that happens strictly, then because the game is constant sum, you'll violate the property that the sum across players of the payoff differential cannot be positive. That implies that either the equilibrium is unique or the gamma i's are equal to 0 for all players, which means that you're always indifferent between choosing the cognition that you're supposed to choose in that equilibrium and the cognition that you're supposed to choose in one of the other equilibria. So that's an example, for example, of a class of games where you can arrive at predictions by checking that this property of expectation conformity holds across all profiles. I will give you some other examples later in the talk. So now I wanted to move away from constant sums, and I wanted to start by talking about a class of cognitive games where cognition is self-directed, meaning that each player cognition affects the player understanding of the game, but not other players' understanding of the game. So in the paper, we consider a few examples along these lines. We consider the case of noisy information acquisition about payoffs. That's probably the class that has received most of attention in the literature. So Tommaso has contributed to that, Muhamet has contributed to it, and many of you have done it. Myatt and Wallace is an example of such games. Christian Hellwig, with Laura Welcome, has some work along these lines. So a lot has been done about noisy information acquisition in games. There are also games where players learn about other players' beliefs. Again, Muhamet has written about it. I'm going to talk about another class of games because I suspect that has received less attention. And this is sparsity in games. Sparsity has been considered primarily in single decision maker problems or in variation economies. To the best of my knowledge, little has been written about sparsity in non-trivial strategic environments. What is sparsity? So sparsity is meant to capture a few things about the underlying decision problem. The first thing that sparsity is meant to capture is a sense of richness of a state space. So it's meant to capture the idea that many environments of interest, the underlying state is a very complicated object. There are so many different dimensions to learn about. Because of that, players are going to pay attention only to a subset of the relevant dimensions, and importantly, reason as if all the other dimensions that they don't pay attention to did not exist. That's what differentiates sparsity from other games of information acquisition. Typically, sparsity is interpreted as a form of boundary rationality. Why? Precisely because players reason as if the dimensions that they have not explored of a state did not exist. What we do here, we provide a particular formalism of sparsity, which is restrictive in many ways, but has the advantage that it is consistent with fully rational behavior by the players, while at the same time capturing the key ingredients, the key spirit of sparsity. So the way we do it is the following. Suppose that players have payoffs that depend on their own action and the action of other in some complex underlying state omega that take the following form. There is a quadratic loss from not aligning a player's action to some statistics of the underlying state, G of omega. And there's also a loss from not aligning a player's own action to a statistics of his opponent's action, and that statistics takes a familiar form of the average of the action of opponents. So here actions live in the real line, so both positive and negative actions are contemplated. The underlying state, it's a complicated animal. So there are k dimensions of this state, and k, capital K, could be infinite. So there are infinitely many things you may learn about that matters for your payoff. each dimension is drawn independently from the others from some distribution fk. Each dimension has 0 expected value and the variance sigma k. The different dimensions are aggregating into a statistics, and this statistics for convenience is linear. It's the sum of the different components. Okay? There's also a natural progression of reasoning, meaning that dimension k can be explored only if all the lower dimensions have been explored first. So think, for example, in certain environments, you can learn about sophisticated stochastic calculus if at least you have been exposed yourself first with everything that is necessary to understand the language of the theorems that is used in that field of mathematics. Okay? This is not necessarily a good assumption in certain environments. There are instances where you can jump, you can decide that you learn about one dimension without having explored other dimension first. That's something that we also discuss in the paper. A player signal in this environment is the subset of the space, of the state space that the player explores. And because of this assumption of the natural progression in reasoning, cognition rho I determines the number of dimensions explored, but not only the number of dimensions determines what are the dimensions explored. Once you fix rho I, which is a natural number, you also fix what are the first rho I dimensions that the player learns about. These dimensions are learned perfectly. All other dimensions are treated as if they didn't exist. I want you to think of player 1 as the follower and player 2 as the leader. So player 2 is the player that goes deeper in the exploration of a state. So that translates into the assumption that rho 2 is greater than rho 1. Remember that in this model, in this formalization, cognition determines the subset of the dimension of a state that are explored. Because of the quadratic loss function that I introduced in the previous slide, the equilibrium actions in the downstream game are very simple. They are linear in the knowledge that the player has acquired. For the follower, the player who's behind in the exploration of the state, the equilibrium action is the sum of the dimensions that have been explored plus 1. So think of 1 as the minimal knowledge that the player are endowed with. So dimension 1, 1 is like a dimension omega 0. It's whatever the players know, but does not require them to engage into cognition. The follower, well, the follower takes an action which is exactly the same action as, excuse me, I misspoke. The leader takes an action which is exactly the same as the action taken by the follower, augmented by the fact that the leader has extra knowledge of a state. But he's the sole player to have that knowledge, so he's responding solely to these extra dimensions, and that's why beta doesn't figure it out when it comes to the sensitivity of the action of this player to this extra knowledge. So why this is a good representation for sparsity? Well, first of all, because it captures the idea that all unexplored dimensions are treated as if they didn't exist. So think about the follower. So when it comes to the follower, he's going to respond to what he has learned, the first rho 1 dimension. Anything that pertains to the other dimension, doesn't matter what's the realization of this other dimension, he's not going to respond to that. Exactly as if the environment was defined by a vector of dimensions which coincides with rho 1, what has been explored by the player himself. Another feature of sparsity is that the player who's ahead in the exploration of a state is able to perfectly predict the opponent's beliefs and actions. This is true in sparsity games, is not true in other games of information acquisition, where you receive, for example, an additive signal of the underlying state. So even if your signal is more precise than your opponent's signals, it may not permit you to perfectly predict the action of your opponents. Finally, the player who's behind in the exploration of a state, this player is going to reason and act as if the opponent's knowledge is the same as hers. So player 1 is going to take exactly the same action as if player 2 also had cognition of row 1. Despite the fact that the player knows, he's a rational player, he knows that his opponent has gone deeper in the exploration of the state, but nonetheless, he's not going to change his behavior. So this is a special formalization, but it captures some of the key ingredients of the sparsity model. And now I want to talk about the role of expectation conformity in this model. Take two profiles, row hat and row, and let these two profiles be such that profile hat has more cognition for both players, and the player who's ahead is always the same. So this is captured by assuming that row 2 hat is greater than row 2 is greater than row 1 hat, which is greater than row 1. When you pick these profiles, which may be justified, for example, by the knowledge that the cognitive cost is lower for player 2 than player 1. So player 2 is expected to always be ahead in the exploration of a state vis-a-vis player 1. Then, irrespective of whether this is a game of strategic complements or strategic substitutes, unilateral expectation of conformity holds for these profiles, strictly for the follower, weakly for the leader. Instead, increasing differences holds as a quality for these profiles, meaning that the payoff differential of going from a lower level of cognition to a higher level of cognition is invariant in the selection of the cognitive level for your opponent. The second part of a proposition is meant to be relevant for environments where the analyst has knowledge of the cognitive costs are the same for both players. So it's likely that the equilibrium is symmetric. What the result is saying is that, well, take two profiles such that the two players have exactly the same cognition, and think of hat as the profile where cognition is the highest. Then unilateral expectation of conformity holds as a quality for this profile, increasing difference holds for complements, and it holds as negative increase in differences if you have substitutes. So what's the intuition? Well, the intuition is that to think about unilateral expectation conformity. For the trivia, for the leader, this is trivial. Why it is trivial? Because the follower's action is invariant to the number of dimensions that are explored solely by the leader. That's one of the features of sparsity. For the follower, is due to the fact that the leader is going to respond more to dimensions that are commonly explored under complements, and is going to respond less to dimensions that are commonly learned under substitutes. In both cases, the follower benefits when the leader anticipates an expansion in cognition by the follower. So in other words, the follower never gains by the leader being surprised by the expansion in cognition. When it comes to increasing differences are equal to 0 in case A. This is trivially so. In case B, this is again due to the fact that exploring more dimensions has higher value when we are jointly explored under complements, and lower value when we are jointly explored under substitutes. Okay, so the result also suggests that if we were to put some structure on the cost, going back to what Tommaso was suggesting in the beginning, based on the proposition that I introduced at the beginning, this seems to suggest that it's likely that the equilibrium is unique when the cost structure is the same across players with substitutes, whereas it's likely that there are multiple symmetric equilibria with complements. And in fact, we can verify that this is the case. So suppose that the cost is separable across the different dimensions. So the total cost is the sum of learning the different dimensions. And suppose that the ratio between the benefit of learning one dimension and its cost decreases with the dimensions and vanishes in the limit. When actions are strategic complements, all pure strategy equilibria are symmetric. Furthermore, there are bounds on cognition, K lower and K upper, where K upper depends on the magnitude of the complementarity in actions, such that any K star between these two bounds can be sustained as a symmetric equilibrium. If there are no external payoff effects, meaning that if there are no variation in the state and or in the action of others that matter for payoff other than what triggers a change in best responses, then all equilibria Pareto ranked, and the player's net payoff are increasing in the depth of knowledge. The equilibria that I described are also robust to the possibility that players select the order by which they learn the different dimensions. Contrast this to the case of substitutes.
Alessandro, sorry,
Yep.
10 minutes more, yeah?
Yep. In the case of substitutes, we exist at most one symmetric equilibrium. The equilibrium exists if this double inequality holds, which essentially guarantees that learning the K dimension jointly is valuable. Learning the K plus one dimension solely is not. In this case, either a symmetric equilibrium does not exist or it's unique. However, there are multiple asymmetric equilibria. The equilibrium payoff of a player who's behind is increasing in her own cognition, and it's invariant in the opponent's cognition. The equilibrium payoff for the player who's ahead in the exploration of a state is decreasing in the opponent's cognition. And if you look at the sum of the two players' payoff, the sum of the two players' payoff is maximal in the equilibrium where the player who's behind learns the least. So I'm going now to talk about a class of games where cognition has a manipulative phase. I'm going to talk about framing in games. I want you to consider the following persuasion game. So player one plays the role of a sender, player two plays the role of the receiver. So this is a game where cognition has an effect on another player understanding of the game. The sender's payoff is increasing in the receiver's action. The receiver payoff is given by quadratic loss with bliss point omega. So this type of formalism has received a lot of attention in persuasion literature and information design. So here the idea is that the sender wants to boost the purchase of the buyer, for example. The buyer wants to do what is right for her. The receiver is endowed with a knowledge of omega. So originally, the receiver knows omega. Problem is that she forgets. The receiver's probability of retaining information about omega depends on how much effort the receiver puts to recollect, row 2, and depends on how much manipulation is undertaken by the sender. So here the cognitive choice of a sender takes the form of a frame that boosts the chances that the receiver recollects positive states. What really matters is that this cognition has asymmetric effects over states that are favorable to the sender, vis-a-vis those that are less favorable, the negative ones. With probability 1 minus r, the receiver does not recollect anything. However, the receiver is not an idiot. The receiver understands that whether he or she recollects depends on the frames that have been used by the sender. So for example, when you go to a store, the fact that you recollect information or not, it depends on what music you're exposed to, whether Christmas music is in place. It depends on whether a particular product is associated with certain images vis-a-vis others. So what's the result here? Well, the result is the following. Take two profiles, row hat and row. Unilateral expectation conformity always holds for these profiles, weakly for the receiver, strictly for the sender. Increasing differences holds for the sender if a certain condition holds, where this condition has to do with the modularity of the probability that the receiver recollects positive information, and also to the extent to which the absence of any recollection varies with investment in memory management made by the receiver. So think about unilateral expectation conformity. Suppose that the receiver does not recollect anything. When you don't recollect anything, but you know that someone has put in place frames to boost your ability to recollect events that are favorable to the sender vis-a-vis the less favorable ones, and if you don't recollect anything, you should conclude that the most likely the state is unfavorable to the sender. The fact that you don't recollect is, other things equal, informative of the state being negative. These are the states where the sender was less likely to engage into manipulation. But then means that if you don't recollect, you're going to respond by taking a very conservative action. Because of that, the incentive for the sender to manipulate are stronger. So this is similar to what has been documented in other signal jamming environments, including career concerns when effort has a multiplicative effect with the state, such as in work that Matthias Duatripon, Ian Jewett, and Jean have done in previous work. So I want to use my remaining 5 minutes, if it's fine for the organizer, to give you at least one example of a game where cognition takes a form different from learning about payoffs. And this is endogenous depth of reasoning. So contrary to what you have seen so far, consider a situation where payoffs are commonly known with no state omega. Cognition in these games defines the number of steps of iterated best responses that a player is able to compute. It's the cognitive capacity of the player. So there's a sequence of mixed actions, alpha k, for each player. Alpha I0 is an anchor, is the action which is expected by the analyst to be selected by a player who engage into the minimal level of cognition. Each subsequent alpha is a best response to the previous alpha of the opponent. So this is exactly what is done in the level K literature. Alpha naught is an anchor. Alpha 1 is the best response to the opponent playing alpha naught. Alpha 2, it's the best response to the opponent playing alpha 1, and so on and so forth. So how do the players play in the downstream game, given the cognition that they undertook, and given the cognition that they expected to have selected, and given the actual cognition of the player? Well, this is very complicated notation that, especially towards the end of the talk, doesn't make your life easy. So let me just say it in words what this is meant to capture. This is meant to capture the idea that a player's action, it's the one identified by the player's depth of reasoning, by the number of steps of iterated best responses computed by a player, unless a player has overshooted. So for example, if I think that Tommaso can do only 2 steps of iterated best responses, and I have done 6, then I also realize that anything that I've done after step 3, it didn't really help me refine my understanding of what is best for me as a best response to what Tommaso is likely to do. So this is a game which is a little bit strange, which is normal that it's going to sound strange because it's a game played by boundary rational players. What are the flavors of this game? Well, one of the flavors of this game is that players understand how changes in cognition affect the way the payoffs are going to move with cognition, even if they're not able to compute perfectly the best responses. Another feature of this game is that when you expand your cognition, you may end up with a lower payoff. Why is that possible? Because expanding your cognition without being able to perfectly identify your best response to the action of your opponents may bring you more far away from the best response relative to a situation where you engage into fewer rounds. So in other words, if you engage into more cognition, you can be trapped into a cognitive loops where you think more about the game, but without really being able to identify what is best for you. This is a feature of the level K model. So we're going to apply our notion of expectation conformity to a class of games that is meant to capture incentives to undercut the opponents, and that has been popularized in some work that has been done by Ariel Rubinstein with co-authors. So in this game, the action...
I've got 2 minutes, yeah.
Yeah, the action set of each player is going to be given by the integers between 11 and 20. Payoffs are as follows. So players are asked to name an integer between 11 and 20. And then you're going to receive a certain number of dollars that are equal to the number that you name. If you match your opponent, you get a boost of 10 more dollars. And if you undercut your opponent exactly by 1 unit, you get an extra boost of X, where X is a large number. Okay. So we apply our notion of expectation conformity to these games, and we can identify forces that shape of the opponent to conform to the expectation of the others. We show that in these games, the difference between the cognition of a leader and the cognition of a follower is at most 1. So either the two players select exactly the same cognition, or the cognition difference is at most 1. And we can use the decomposition into unilateral expectation conformity and increasing differences in order to shed light on what are the incentives for a player to expand her cognition in response to the beliefs that the player has about the cognition of opponent and the actual choice of cognition of opponents. So I'm going to wrap up by summarizing where we stand in our project. So we develop a notion of expectation conformity for strategic reasoning, who really captures the interaction between two synergies. The idea that players choose cognition in a way that responds to the opponent's expectation about their own cognition, but also they choose the cognitive posture by responding to beliefs that they have about the opponent's actual cognition. The interaction between these two synergies has an important role for the determinacy of equilibria, for the sensitivity of cognition to the type of strategic interaction, complements vis-a-vis substitutes, and in our view has the merit that it can shed light on how players choose their cognition even away from the fixed points. So the entire analysis proceeds through a diff and diff decomposition that does not require that you apply that decomposition to the fixed points. And in fact, for comparative static analysis, as it is well known to the game theorist, reasoning at the equilibrium is often misleading. So comparative statics are superior most of the time when performed away from the fixed points. Fixed points has its own properties that can misguide you in understanding what are the driving forces. So the diff and diff decomposition that we propose has the advantage that it can be useful not only for equilibrium analysis, but also to shed light on the primitive forces at play. In the paper, we also talk about noise information acquisition, which is the case that has received most of the attention in the literature. I didn't have the time to cover it. We talk about espionage, when you're trying to learn not about the primitive state, but about the beliefs that other players have about their own payoff. We also talk about counterintelligence, such as when you put in place defensive measures to make it difficult for your opponents to understand your own view of a game. And we also talk about the generalized career concern models as a class of games where cognition is manipulative and shares some of the ingredients with the framing games that I've seen, that I've shown you a moment ago. So I have one more slide that by far is the most important one, which is this one. So thanks a lot for listening to me, and I look forward to the reaction by the panelists, and I'm very happy to answer any questions that you may have. So thanks a lot to everyone.
Thank you. Thanks a lot, Alessandro. Thanks a lot to everyone. So the floor is open for questions. We have the Q&A session. Feel free to jump in and
start with the panelists if they have anything to add.
Yeah, so I had like, a question about like how you think about this, like especially the applications that you chose about, like cognition when actually people are going to be boundedly rational, the game that they are going to play afterwards.
Yes.
So especially the choice of how much to recognize.
That's one of the, yeah, we discussed a little bit of that in the paper. It's a delicate point, but it's a point that is sort of unavoidable if you want to endogenize sophistication with boundedly rational players. So this is something that we touch upon in the context of the level K model. So the formalism that we follow here is the following. So we assume that the players understand the forces that shape the connection between the sophistication and the payoffs. So they may not be able to perfectly predict the best responses, but they understand the direction by which an expansion in cognition by themselves and or by the opponents impact the payoffs. And that by itself may or may not disturb you. So depending on the particular application you have in mind, you may find it unappealing, the assumption that players realize how payoffs move with sophistication without being able to fully work out the best responses. Or you may find it that finding the best responses can be very demanding. Understanding the connection between sophistication and payoffs maybe is not so demanding. So we leave it to the to the audience, we leave it to the reader, we leave it to the the applied theorists to decide what is appropriate depending on the context and the examination. The best I can say is that this is a tension that no matter what you're going to encounter, if you want to have two things at once: bounded rationality and endogenous sophistication. It's something which is also discussed in previous work by Alaoui and Penta. These are the first authors to endogenize the degree of sophistication in the level K model. They do it with a type of cost and benefits analysis that does not permit to talk about beliefs over the sophistication of opponents. That's the key point of departure with respect to what we do. But they also take a stand on how V changes with actual and perceived cognition. You have to. And they also realize that in these games, expanding cognition may bring you away from the highest possible level that you can attain, vis-a-vis a situation where you content yourself with lower cognition. It's a feature of bounded rationality, like thinking more about a game, but not enough to predict the action of your opponent. It can drift you away from your ability to identify what is best for you.
I have a somewhat related question. So in the talk, you're basically presenting these two models. You have a broad notion of cognition, and then you have basically these two models. Like the first one, where you stick with the information acquisition interpretation.
Broadly meant, yeah.
The second one is kind of like a very interesting, but also looks a bit like a different model.
Yeah.
So I was wondering also maybe to address these issues, if you've thought about using the first class of models, the one with information acquisition, to think about, strategic reasoning, strategic uncertainty. What I have in mind is that, it is often the case that, in some sense, strategic uncertainty, payoff uncertainty are blurred in many papers. And in the application with the level K, in some sense, you had exactly similar to sparsity. You had a bit that flavor. So, I was wondering if you've thought about like just using the first class, but then try to kind of like reinterpret it maybe in a more concrete way in terms of like.
Yeah, thanks a lot, Tommaso. This is an interesting angle. So I should talk for myself, but my understanding of this connection is still limited in the sense that it's there are things in common between sparsity and level K. But I'm still, understanding of a connection and the process of understanding what is shared by the two formalism and what makes the two different. So there are things that, as you catch, are in common. And the sparsity model, the version that we propose, has the advantage of it, it's consistent with full rationality of the players. It's not always like that. So there are authors that have proposed notion of sparsity that are paired with bounded rationality, but the particular one that we proposed in the paper, it's consistent where the players are being fully rational, and nonetheless it captures the spirit of it. And you're right, there are things that sparsity has in common with level K. In particular, this idea of not necessarily responding to an expansion of cognition by your opponent. So when in the sparsity model, when I've learned row 1 dimensions and expect Muhamet to be ahead of me and further expand his cognition by going from row 2 to row 2 prime, I don't change my response. That's a feature of sparsity. I understand that he's going deeper in his exploration of a game, but I maintain my action exactly the same, despite the fact that I realize that he's expanding his knowledge. That's one of the features of a sparsity model, which is also shared by level K. In level K, once I hit my capacity, I can expect Muhamet to be way ahead of me in the understanding of iterative-based responses, or I can expect him to be little ahead of me, and in both cases, I'm going to behave exactly the same. So certain ingredients are shared between the two, but there is one aspect that is not in common. In the sparsity model, the value function is always weakly increasing in cognition. It's never the case that the player expands her cognition and lands at a lower payoff. It cannot happen. In the level K model, that can happen. And this is something that was recognized by Alaoui and Painter. It's a feature of the fact that the computing is a finite number of rounds of iterative-based responses, but not going all the way to predicting what is your maximizing action. It can actually yield a lower payoff to the player rather than a situation where you perform fewer steps of iterative-based responses. So there are things in common, but there are also differences. Yeah. So I should not monopolize the conversation. Jean, feel free to,
I think you said it very well. I mean, the sparsity model is very clean in that it captures intuition, and there is not that much difference between bounded rationality and the and rationality in that case. The level case, of course, you explained that well. It's difficult because you have a value function, and you can perfectly compute this value function without computing what you're going to do if you learn a little bit more. So, and what we should do at some point, I mean, we as a profession, is to try to understand when this assumption is not too strong and when it's really strong. And also on the value function decreasing, when the leader expands more cognition. Yes, I mean, but that's really irrational in a sense, because you realize that, Alessandro, you should realize that I'm level 2 and you're level 5. And, given that that, you should, you can go to level 5 if it's free, but, you're going to throw away the new information if you are anything close to rational. So it's a difficult model in a sense. It's a very interesting model, I think, but we still need to go further and try to understand when there's a big loss of generality and when it's not, and it's a good approximation, basically.
Yeah, I think Jean is referring to this part of it. Unfortunately, I was a little bit late, so I couldn't cover at the pace that would have been understandable. But what can happen is that the leader, the player who goes deeper in the understanding of the sequence of iterative-based responses, may end up undercutting the opponents by too much. So these are games that are meant to capture the strategic situation faced by a firm that has a set of loyalists that is going to attract no matter what, and then there's a segment of a market which is contestable. If you match your opponent's price, you're going to share equally the contestable segment of a market. If you undercut your opponent by a little, you're going to profit a lot because you conquer completely the contestable segment of a market. But if you undercut by too much, then the losses that you incur inframarginally more than compensate for the fact that you expand your market, so your payoff decline. And in this game, they decline a lot because you are not entitled of neither of these two bonuses when you undercut your opponent by more than one. So if you're not able to perfectly predict your opponent's action, you may end up undercutting too much. When your opponent increases his cognition, he's going to lower the number that he calls. So that's going to favor you. So it may surprise you because you're looking, so how do I gain by my opponent lowering her price? Well, you gain by your opponent lowering your price because you are cutting your price too much to start with. So that's one of the features of this game proposed by Rubinstein and co-authors. In general, level K, it has appeal. It can also disturb a lot. It's something that is receiving, has always been very popular among game theorists, but I was surprised to see that even macroeconomists use level K model quite extensively these days. Some people at MIT have played with it, and it's something that is becoming more widespread. So it's a model that has its own limitations. Conceptually, it's difficult to digest it. So when I see, the reaction in the face of Muhamet, I can tell the discomfort. But Muhamet is a fully rational player, so he cannot understand what the heck I'm talking about. Well, it's difficult for him to appreciate what this model is meant to capture. But there are instances where the level K model is believed to be a decent description of the cognition that the players engage in. And then what we were trying to do in this part of the paper is to shed light on what happens in these games when you not only endogenize cognition, like in Aloe and Pinta, but you try to explain the endogeneity along the lines of players predicting the cognition of others, but also players adapting to the expectation of others about their own cognition. So we think that this decomposition of it we push throughout the entire paper of unilateral expectation conformity, interacting with increasing differences. It's relevant not just for games where cognition is information acquisition or sparsity. It may also be relevant for games where cognition takes other forms. And I think actually, if anything, in the future, it would be nice to extend it even to other forms of cognition that are neither information acquisition, not level K reasoning.
Any other comments from the panelists?
Happy to take other questions, of course.
I think it's time for us to formally stop the recording and then move to the informal part.
Thanks again to the organizers for organizing this entire stream of presentations, especially these days where there are so many negative things related to the virus. So this is one of the things that stand out as being an improvement vis-a-vis what we used to have in the past. So thanks again for not just inviting us, but setting in place this workshop.
Thanks so much.
Thanks a lot to everyone. Yeah, thanks to everyone who is accepting coming to our series.